Now I want to talk about the area between polar curves. All right, essentially the area between polar curves is I just have to figure out where those curves intersect and what my outside radius is at any particular point. So let's look at example 4. Suppose I want the area inside of both r equal cosine theta and r equals sine theta. Well, r equals sine theta is graphed in green here because when theta is 0, I'm at 0. At pi halves, I'm up here. And at pi, I'm back at the bottom again. R equal cosine theta is also a circle, but it's rotated a little bit. At 0, cosine of 0 is 1, so I'm there. At pi, I am there. At pi halves, I am there. And then at pi, cosine of pi is minus 1. It would be over here, but since the radius is negative, it gets reflected, recall. And so I go that way. And in fact, let's put in a few arrows here to indicate how I'm moving. Okay, so the area inside of both turns out to be this little piece in the middle there that I've put in blue. All right, so what's the point? The point is that if I want to sweep starting at 0, then this area is defined by which curve? R equals sine theta up until this point. And then if I continue sweeping, the area is defined by the other curve, r equal cosine theta. So let's figure out where we have an intersection. Well, intersections of polar curves is a little tricky because polar coordinates are not unique. In this case, though, so the first thing we do is try to solve sine theta equal cosine theta. We set the r's equal and see if we get anything there. Well, if cosine theta is sine theta, then I could divide everything by cosine theta. I get sine theta over cosine theta is 1. And of course, sine theta over cosine theta is tangent theta. So I'm interested in where tangent theta is 1. And that happens at lots of places, of course. But in particular, it happens when theta is pi over 4. And we find at pi over 4, on this curve I'm here, and on this curve I'm here. Sometimes curves can intersect, but not for the same theta, again, because polar coordinates are not unique, and in which case life gets a little tricky. All right, so what I'm saying is then, as theta runs from 0 to pi over 4, this piece, and think of this radial arm here sweeping it out. I sweep out exactly half the area by the symmetry as I go from 0 to pi over 4. And what is my outside curve? It's r equals sine theta, right? So down here, the area is, remember the integral of dA, and also remember that dA is what from last time? R squared over 2. So if I want to sweep out half the area here, it's going to be what? R squared, which there's my function. So sine squared theta over 2 d theta as 0 as theta goes from 0 to pi over 4. Plus, and then I have to add this other piece if I want, which would be starting at pi over 4 and ending at pi halves. Notice it's the red curve. That's my boundary. So it's going to be cosine squared theta over 2 d theta as theta goes from pi over 4 rather, to pi halves. Now, if you notice the symmetry of the problem, I could just go 0 to pi over 4 and multiply by 2 of the green curve, sine squared theta over 2 d theta, or I could sweep out this other piece, which would happen from pi over 4 to pi over 2, cosine squared theta over 2 d theta, and multiply by 2. All right, we've done some integrals like this before. It involves double angle. If you want to finish it, you can. I'm going to go ahead and look at the next example. All right, suppose I want to find the area inside of one curve, r equals sine or 2 sine theta, but outside of another curve, r equals 1. Now, r equals 1 is what? It's a circle radius 1 centered at the origin, so it looks like this. R is equal to 2 sine theta is, of course, a circle here that ends up to have diameter 2, right? So if I want it inside of this one, but outside of that one, it's what I've got in green, all right? So what's the point? The point is, first we have to figure out where these intersections are, and we do that by, to begin with, I can set the r as equal. 1 is equal to 2 sine theta. Sine theta is a half. Where does that happen? At pi over 6 and 5 pi over 6. It happens at a lot of other places as well, but those turn out to be the ones we're interested in. All right, so my area actually starts picking up at pi over 6, and it's going to end at 5 pi over 6. Therefore, it's going to be the integral from pi over 6 to 5 pi over 6 of what? Well, I could compute this whole, the area of this curve from pi over 6 to 5 pi over 6, and I could subtract the area of this curve in here from pi over 6 to 5 pi over 6. And that's the way I write it here, right? I go from pi over 6 to 5 pi over 6 of this outside curve 2 sine theta squared over 2 d theta. What does that give me? That gives me actually the area of this piece in here as well as this piece out here. And then I subtract the area of this inside part. And the inside part is r is equal to 1, so I stick in r squared over 2, recall, 1 squared over 2 d theta, pi over 6 to 5 pi over 6. So I take this outside area, subtract the inside area. Notice my limits of integration happen to be the same, so I could combine it into one integral if I want, and just have this piece subtract this piece. And there I have it. That's the area inside of this curve, but outside of that curve. And again, if you want to compute it, I'll leave that up to you. Basic integration techniques. Now, what have we learned from this example? Well, in general, when you're computing the area between polar curves, here's the picture. The outside polar curve is r is equal to f1 of theta. That is, it's the larger radius. The inside curve, f2 of theta. If I want to compute the area between them from say angle alpha 1 to angle alpha 2, it simply is what? The integral from alpha 1 to alpha 2 of the outside radius squared, f1 squared of theta, minus the inside radius squared, f2 squared of theta, all divided by 2 d theta. And that's the way you would handle something like that, where you want it inside of r equal f1 of theta, but outside of r equal f2 of theta. And that's exactly the formula that we ended up with over there. Hope everybody is doing fine. Bye.